In this problem, we have a massless bar that's pivoted on the wall here and is hitting the floor, and everything is frictionless. It's 5 meters in length, 4 meters height, 3 meters across. That's nice. 3, 4, 5 triangle. No friction on the floor, and we're going to apply a 90 Newton force to the right. So this is very similar to, say, putting a board underneath some object that is fairly vertical here, and then giving it a kick. You kind of kick the end of this thing, and you can actually get very large forces upward because of the nature of how this works. So hopefully you have the picture here. Well, the sum of the forces in the x direction, 0, obviously. So the force in the x direction of the pivot on the bar is just going to have to compensate for the 90 newtons here. So it has to push backward with 90 newtons. So there it is. Then, this is going to take a little bit of mental adjustment on our part here. I'm going to consider that we're pivoting about the floor and not pivoting here on the wall. You might say, why do that? There's no necessary reason, but it's just as valid to pivot from this point as it is here. When you're pushing this to the right, keep in mind, this is an equilibrium. This thing isn't moving. It's rigidly against the wall, and you're just putting this force. And so you could consider the pivot point either place just totally, with total validity, of course. So equal and opposite torques. In the counterclockwise direction, what do we have? If we pivot about this point, then counterclockwise is this way, right? This way. That means the force here acting around in the counterclockwise direction. So basically we have a force outward like this, across what? Well, if you're pivoting from this point, the moment arm is this dimension. It's the 4 meters. So 4 meters times this force of the pivot against the bar to the left gives us the counterclockwise torque. So that's force times length vertical. I'm calling this the vertical length of the bar equals the clockwise torque. Now, the clockwise torque, what's making it go this way? Well, what's making it go this way is, with respect to this point, is the fact that as we shove up on this thing, there's a vertical force acting down. This vertical force of the pivot on the bar across the 3 meters. That gives us a clockwise torque about this point here. You found this? So we have force in the y direction times the length in the horizontal. So 90 times 4, see the force to do counterclockwise is 90, it's just the opposite of this, across 4 meters equals the force in question times 3 meters. And we can easily solve for that force, which turns out to be 120 newtons. So 120 newtons in this direction across 3 meters, pivoting here, is equal to 90 newtons this way across 4 meters. Now you could do this problem where you're pivoting about this point and you'd get the same results. And now we do a very important problem type because it involves a ladder, and the question is whether the ladder will slip as an object progresses its way upward. And the object in question is very important as well, for it is a lonely wolf who's going to be endeavoring to get to the top to howl at the moon. Yes, the lonely cry of the wolf, the call of the wild, takes me back to Alaska in the 50 below nights with the full moon, and the resonating wail of that wolf reverberating through the canyons. Well, some other particulars. It's 200 Newton ladder, 800 Newton wolf. It's frictionless against the wall, but it's a coefficient of friction of 0.4 here on the ground. So as the wolf progresses up the ladder, you might be able to have an intuition as to the change that happens. Is it easier for the ladder to maintain its equilibrium condition down toward the bottom or toward the top where there's no friction? And you may have the intuition that it's easier at the bottom, and you would be right. So as you go toward the top, the tendency to slip increases. Well, let's see if the wolf will make it to the top. So we have a 4-meter height. It's a 3, 4, 5 triangle. Free body on this ladder. So we place the ladder on a y-axis coordinate system. Now 1.5 meters from the base here is halfway, right? This is 3 meters across here. So 1.5 meters is the halfway point. The center of gravity exists at that halfway point, so that's where the center of gravity is. So 200 newtons acts 1.5 meters from the pivot, at least that particular pivot. This particular pivot here, y and x equal to 0. And then at some distance d that the wolf progresses through up the ladder, we have his weight, 800 newtons, and that distance is 3/5 d. So if we think of this triangle here, really d times the sine of the angle of this angle, which is also this angle over here. Sine of that angle is 3/5. So 3/5 times d will give you this distance across here. All right. Now we have normal from the ground pushing upward, and we have the friction from the ground pushing to the right, and we have the wall shoving to the left. But because there's no friction over here, there's not going to be any vertical force of this part of the ladder against the wall, or more particularly the wall against the ladder, which is the important thing. So I think I have the free body fully specified here with all the forces. Some of the forces in the x cancel, so the friction on the ground, from the ground on the ladder, is equal to the normal force of the wall pushing back on the ladder, since none of these forces have an x component. Therefore, we have the friction force on the ground, which is mu normal. Well, the normal is ng, and mu is 0.4. So that's going to be equal to the wall force shoving backward. So that's an equation that's very important. And now we're going to have another equation from the y forces are 0. So what's going on in the y? Well, we have this normal force of the ground pushing up. That's exactly equal to the weight of the ladder and the weight of the wolf. So that's 1,000. And so we have that the normal force of the ground on the ladder is 1,000 newtons. Well, given that, since we have 0.4 times that normal is the normal of the wall, we can sub in and get the wall force as well. Thus, the normal of the wall on the ladder, 400 newtons. And therefore, the friction force of the ground on the ladder is also 400 newtons, equal and opposite. So here's our picture again, and we need to maintain equilibrium. So we must satisfy that the sum of the torques is 0 as well. If we want to minimize our number of equations, make our problem as simple as it can be, it's logical to pick a point of rotation, a pivot point, where the line of action of as many forces as possible goes through that pivot point. In other words, right here, the line of action of both of these forces goes through the pivot point, therefore the torques are 0. So those terms will be 0, and we'll just have the other terms to deal with. So that is a nice logical choice. Picking the ground as a pivot point. Equate counterclockwise and clockwise torques. So counterclockwise, the only thing that's counterclockwise is going to be the wall force through that 4-meter distance. So 4 NW equals clockwise 200 and 800 through their respective distances of 1.5 and 0.6x. So let's write that out. 1.5 times 200, 0.6x, 800. So we can solve for x. We already know the normal of the wall is 400, so that's just 1600 minus 300 over 480. 0.6 times 800. 2.71 meters. That is the answer to the question. That's how far the poor wolf makes it up the ladder before the torques are no longer equal and opposite, and we have a dynamical problem where the ladder rotates and the poor wolf goes down. Now, what's the force of the ground on the ladder? The ground force on the ladder in this case. We have friction and we have the normal force. So this is real simple. 1,000 newtons and 400 newtons and an angle. So that force is 1077 newtons, and the angle just comes out to be 68 degrees. You may want to ask why not 53.1, which would be the angle from the ground to the ladder itself. And if that happened, that would mean instead of at 68 degrees, we have a rather shallower angle for the force, which would increase the size of the wall normal, which would then increase that torque, and you'd have a net counterclockwise torque. So the net result is the poor wolf is not going to be able to howl at the moon tonight, but there will come a night where he will have his day and his say. And the pack will join him as well in a melodious chorus of howls. Let's do one more problem of this genre. This will be kind of fun. We have a football player that happens to be finding himself hanging off the end of a rope and his foot touching a wall. And the dimensions of this problem are given. 20-degree angle of the rope makes with the wall. The application point is toward the top of his body, and there's a 60-degree angle from the wall to the line that his body makes with the wall. So what we're going to do is find the tension in the rope and the force that the wall exerts on his feet here. So we equate clockwise and counterclockwise torques, and that's going to be our main scheme here. And then forces are equal, all add up to 0 as well. So the free body diagram we got to do very carefully. We're going to model this football player here as basically a plank, or I'm showing it as a uniform structure here. Turns out it's not really uniform. The problem tells us what's going on, namely that the center of gravity is 1.2 meters from one end, and the rope acts at a different point, but the 900 newtons acts at 1.2 meters from the pivot point, so that's not in the center. And there's a 60-degree angle here from the vertical and his body, right? Now, 1.5 meters from the pivot point is where the rope is applied, the tension that we're looking for. And of course, with respect to the vertical, that's 20 degrees. Well, if this is 60 degrees and this is 20 degrees, you could think of this as being like alternate interior, right? And that would be 60. So what's this angle? The angle that the tension makes with respect to his body, and that's going to be 40. So that's the basic geometry. And now let's apply some forces. We got the wall shoving outward, and let's see, just by looking at this, we would expect we're trying to rotate counterclockwise, and so the force of friction is going to shove up on his feet to keep him from rotating, right? That would make sense, I would think. Any other force? Well, and that's going to be the point that we consider the pivot point to be. So now 1.5 t sine of 40. So we have 1.5 meters times the perpendicular part of the tension, which is this tension, times the sine of 40 gives us this much applied right here. So that's the counterclockwise torque. Clockwise torque, of course, we picked this point to rotate about, or considered the pivot point, because these forces go through and don't provide any torque. We have 1.2 meters times 900, but we want the perpendicular part of that 900, so that's going to be sine of 60. So 900 sine of 60. And let's see, is there anything else? Well, yes, we need to consider, well, what else do we need to consider? Anything? No, that's it. So the tension is easily solved. We just plug the numbers in from above and we get 970 newtons. There's our tension. Now, the forces X and Y add up to 0 in both directions. So we have that the normal force, this force here, is going to be equal to the horizontal part of the tension. Well, that's just, we have with the vertical, it's 20 degrees. So that's just T sine of 20. So that's 332 newtons. That's the normal force. And then friction, this force here, plus T cosine of 20, the vertical part of the tension, has to equal the 900, the weight. So from here, we can get friction, which is 900 newtons. That would be minus this thing, minus T cosine of 20. That gives us minus 11.5 newtons. Well, now this is curious. 11.5 newtons with a negative in front. What does a negative mean? As you've come to know and learn, a negative in front of a number like this, a measurement, a result, really means that we have chosen the wrong direction. So whereas we thought the friction was acting up, it's actually acting downward. That seems a little strange. Friction is actually acting down. Well, we can resolve this when we realize, probably looking at the free body diagram over here, when you realize that the center of gravity is pretty close to the line of action of the tension. So if you think of the center of gravity here, acting on this board, the amount of torque counterclockwise, rotating about this way, just from the football player himself. Since the center of gravity here, there's not much of a tendency to twist counterclockwise. So that's not going to be wouldn't be a very large force upward over here in the first place, assuming it was upward. Whereas we have this very large force over here that has a very large component in the direction of the football player shoving into the wall. Right? So the part of this tension shoving into the wall is large. And if you think of the part of that that's acting upward, again, shoving the football player into the wall, results in the wall having to push down on the football player's foot, which turns out to be a greater force than the tendency, from the center of gravity here to rotate counterclockwise and pull his feet down, and therefore the wall would have to push up. So I don't know if that all made sense, but it kind of relates primarily to where his center of gravity is, which is high up here. And so the wall actually has to push downward on the football player. The wall has to push downward on the football player in order to keep him in equilibrium.